Hello, it's What the Doodle here, and in today's session I wanted to talk about distributed file systems. I find them absolutely amazing and fascinating. And one of the original papers, if you could call it the seminal papers, was by Google, and it was called the Google file system. I have it right here. And of course, what I'll do is I'll put a link in the description so you guys can have a read of it. I would highly, highly recommend it. Of course, I'm not going to read through this here, but based off the back of this, things like the Hadoop distributed file system, or HDFS, was then inspired from that, and then later on things like Amazon S3. Now, Amazon S3 is very interesting because it has become effectively a de facto standard. So whichever cloud provider you go to, whether that is Azure, Google, or even Amazon, because of course Amazon created it, even DigitalOcean, and there are many others, practically everybody understands S3. It has become almost like an open standard. I guess I presume it is an open standard. In fact, let's confirm those things actually. So let's just see which. Yeah, so of course, yeah, okay, so Google File System GFS was in 2003 and HDFS was in 2006, and actually is let's just see, is AWS S3 a standard? It's not a standard. It's a proprietary cloud storage service offered by Amazon. Blah blah blah. While it has become widely used in popular solution, it does not adhere to any industry-wide standard for object storage. S3 provides its own API and protocols for interfacing with its services. However, many other cloud storage providers have adopted similar concepts and interfaces, making it easier for users to transition between different platforms. In essence, while S3 is a very influential service, it's not a standard in the same way that protocols like HTTP or FTP are. Okay, so it is not a standard per se. However, the actual API itself has been adopted. So everybody and the cloud providers have done that because of the fact that they want to allow their various different customers to be able to transition across different cloud providers. And so it's not a standard in as an actual standard. However, it has been widely adopted. So I would say it is obviously semantically there are, if you want to be very technical about it, it's not a standard, which is a bit of a shame. But however, practically speaking, it's as close to a stand. It is close to a standard. So anyway, going back to here, I'm not going to go through that paper in detail. Obviously, they talk about that implementation at a very granular level, and it is definitely worth a read. However, I just wanted to break it down in terms of sort of my understanding of it, and partly because there is this whole thing. I don't tend to understand something until I've actually built it. It's sometimes they call this the not invented here syndrome, but I think I think having NIH is important if you want to actually learn how something actually works by actually building one of these things. And so I would like to actually build a very simplistic, not a full blown one, but a very simplistic version of that. And so, in my understanding of the way this whole distributed file system works, or GFS, and sort of systems that have been inspired by it thereafter, you essentially have a sort of a main entry point or a master server, or sort of the main controller, if you like, in that cluster, and then you have a set of workers or nodes, as they're called, worker nodes or something like that. I'm going to call them W just for shorthand, and let's say we'll call this 1, and there will be a bunch of these, so let's copy this a few times. So let's put one here. Okay, let's call this worker node 2, and then another one, and in sort of mathematical style notation we'll call this n to denote the nth number, because there'll be a number of these. Now, another thing to keep in mind, let's just put that here. I'll put it here, is to understand that these sets let's just align that up here. Yeah. So let's put a text here. So there is something to understand, is that these worker nodes are essentially elastic storage. And what we mean by that is that these worker nodes, there could be more, could be added. Some of them may crash and may be taken offline, and they may be rotated. So these are elastic, essentially. Elastic storage. So that is one of the brilliant features of a distributed file system, is that you can scale out. And what that means is that rather than having a single server with a very large amount of storage, you have lots of small off-the-shelf servers, and they just keep adding them. And you can essentially this is how you can have massive amounts of cloud storage, essentially, by distributing it. Of course, in terms of the performance, that also scales as well. So it isn't just about storage, it's also about the performance of that when you have a lot more machines in terms of write, in terms of read and write as well. So what is the purpose of these two main, if you like, main modes of servers, if you like? So the point of the master is essentially, let's just put a text here. The point of it really is to be a meta store, because that's what it is. It's a metadata store. That is its main function. It's the thing that holds information. So it's almost like a miniature database of the entire storage of all the objects, all of the files that are across the network, across the cluster. So, and the way that works is, so let's draw a few lines here to show the data communication lines that happen. So let's connect them up, and add another one. Okay, so what happens is when a file is added to a distributed system, essentially they are split, chopped up, and essentially distributed across a bunch of worker nodes. So sometimes they're called data nodes, sometimes, I think in the paper they call them chunk servers or whatnot. So they have various different names, but the principle is the same. So in essence, you have a file and you split up. So let's see that in sort of a little bit more detail how that could be. So imagine this is a file, if you like. This is a certain file, and what we'll do is we essentially chop it up. So what we'll do is we will chop this file up. So we take a file, we chop it up. Oops, and let's do another one. Okay, so when we'll call this chunk, so we can call it, let's say C1 chunk 1, and let's call this chunk 2, and chunk 3, and say chunk 4. Okay, so when you get a file, you split it up, and you split it up based on a particular size. I think in the Google paper it was something like 64 kilobytes. So you take a file and you chop it up into 64 kilobyte chunks, and thereafter you distribute that chunk across all the various different chunk servers or workers or whatever you want to call them. And you don't just split them up and put them randomly across here. You have to, there's something known as let me put it here. Let me put that here. So there's something known as the replication factor. So that essentially means how many redundant copies do you want to have? How resilient do you want to make it? Of course, the higher the replication factor, that essentially means, so say for example you have one of those chunks C1. If the replication factor is 2, then that means there has to be at least 2 copies of that C1 chunk distributed across all of the various chunk servers that you have, or the workers that you have. It has to be split across. And obviously, the higher the factor, the more robust it is. It means, of course, if you have a lot more copies of it, then those servers can crash, and a few servers crashing will not make much of a difference, because statistically it will be guaranteed that it will be available across. So it can be very resilient and robust against failures. Of course, it is a balancing act. You don't want to set it too high, and you certainly don't want to set it too low. So I believe the replication factor for GFS, Google File System, was, according to their paper, they set it to 3. I think that's the default. So that essentially means every single chunk is copied, at least a minimum of 3 times. Of course, you have other things. When a server goes down, then the master server is aware that a particular worker node or a chunk server has gone offline, and so you have things like rebalancing, which essentially means in order to keep that replicate, because the replication factor would then drop, because it will mean that, let's say C1 was on worker node 2 and worker node 2 died, then of course that in terms of what the replication factor for C1 is would drop, and you'd have to bring it back up, and you'd do that by reshuffling, so that you'd have C1 copied onto another, you'd distribute it to another server, so that it meets the replication factor, in other words. So to sort of drill down a little bit further, how would this metastore actually look like? So we've talked about the replication factor. We talked about the fact that it's elastic. And if we have a look at the metastore itself, we know that you have a file and you chop it up. So you can imagine, if you were to, let's just define this as sort of in terms of a JSON object, it essentially is just an array of each of the chunks. So, and the chunks themselves will be something like, you'll have an ID. So we can call this, for example, C1, that chunk, as we mentioned. And then we would have essentially a bunch of hosts. And hosts are essentially just IP addresses of each of these. So each of these workers or chunk servers would have their own IP address. And it would be something like this. So let's just say 10.0.0.10. And it might be available on another worker node or another chunk server on 11, and then this would repeat. So this is just only one chunk. So we would want something like the actual object would be, so this would be like file. We want the actual file name. So let's say we have a file called bob.txt, and then we have the actual chunks meta information. And then it would essentially just be this array here. Yeah. Can we transform this? Yeah. So that now, so you can imagine the metadata that is stored for each file. So this metadata that's stored for each file as a data structure is fairly easy. Well, of course, this isn't all of the granular details. If you go through the paper, there's a lot more to sort. But at a very top level, it would be something. The metadata would be something like this, where you have, so the file object, you have the file name. So obviously that you need to know what the name of the file is, and you have the chunks, and the chunks themselves. Each chunk will have an ID. So when you split each of these when you split that Bob file, if you like, into 4 different sections or 4 different chunks, you have to give each of the chunk some kind of ID to reference it. To be honest, I would probably just, instead of generating an ID, I'd probably just create the hash of it. I'm not sure if that's what it does in the paper, but if you read in detail, that they probably go into a little bit more detail about that. So you have the ID, and then afterwards, related to that, are the hosts. And this is where, in terms of the implementation, part of the master's job is to figure out, based on the replication factor, so this, where to actually place that particular chunk, that specific chunk for this file, where to place them. And all of this is important because obviously this whole meta store data is essentially a database, but a database, they do it in memory. And the reason they do that, of course, there are other things, mechanisms, for example, behind the scenes, where they will take certain snapshot of the in-memory representation or the in-memory database, and then they will snapshot it for reasons like if you restart the metadata or the master server, if it's rebooted or crashed or restarts, then you need to be, if you lose the metadata store, then you lose essentially everything, because you don't know where you wouldn't know where all the chunks are, because without the metadata store, you you lose everything essentially. You don't physically lose the data, but it would be very difficult to work backwards because you wouldn't know which chunks constitute what, because that's kind of the index, if you like. So anyway, if we go back here, so as I mentioned, so this is a very top level, high level overview of how that would happen, and we need to think about in terms of a few, because obviously now they will have a few key top level APIs if you like sort of interface to talk to us. But one thing you'd need is a client, and a client is essentially the thing that interfaces. So if you have a user, so let's have a user here. Let's look for a user. Okay, so if we drop a user here, so we have a actually let's use let's get rid of that one. So if you have a user who wants to essentially interact with this distributed file system, then they can't do it directly. And if we go back to our shapes, so when a user interacts with the, what's happened here? Let's delete that. So when this user wants to interact, they would go through a client essentially. Let's just straighten that up a little bit. And the client itself would then talk to the master. So it would say, hey, I want this particular file. Let's just stick that there, delete that, and let's straighten this up a little bit. And let's straighten this up. Okay, well, I'm not sure where this came from. Okay. So you essentially have a user. The user talks to a client in terms of getting a file or deleting a file or whatever the file operation is. And then that talks to the master. The master itself then, let's say as an example, it says, I want, get me file Bob. I want to read file Bob. So it goes to the client. The client would request to the master, can you give me Bob or bob.txt? And obviously this is essentially a database. It would look in the meta store for Bob, and it would return something like this metadata information to the client. The client then knows, obviously it's not just this chunk one. It will have chunk one. It will have all the 4 chunks. So if we go back here, I have not added it in because I'm lazy, but that's just, you have to understand that the chunks would contain it would contain all of them, all of the chunks needed for that particular file. So the client would know. The client would then have all the information it needs, that it would know where all these chunks are, and there'll be multiple options. So chunk 1 may be available on worker 1 and maybe also available on worker nth or wherever. It would then, so if we do another line, what would then happen is the client would directly make the calls to each of the workers or the chunk servers. So let's add another one. We add it here. And you can imagine it could be, it might connect to a bunch of them. And it will then pull back all the chunks that it needs and then be able to reconstitute that file, stitch all the files together, and then return that back to the user. So that's, it doesn't talk to the master. The master doesn't then pull it. It's the client actually connects directly, because, as I say, you have that metadata information. The purpose for the metastore doesn't need to do anything further, because it's just a pointer, if you like. And this makes it really scalable, because you can imagine if you have multiple clients connecting to it, by having it, that replication factor also helps in terms of performance as well, because each client can, the chunk, for example, even if they wanted to read the same file, because it's distributed across, because of the replication factor, when a client picks a particular chunk that they want to read, they can read it. They can just pick a random chunk to pick it from, because they'll have multiple options. Because of the replication factor, a chunk will be available in that more than one chunk server essentially. And so there, in terms of scalability, it will be a lot, because obviously it's not just, it doesn't have to do it in serial, for example. That client could make in parallel. So if there's, in this example, there's split into 4 different chunks. So in parallel, it can make calls to 4 different servers, in concurrently, and then pull down those files and then stitch it back together again. So you can have quite a lot of performance and scalability. But of course, that isn't the main aspect of it. That isn't the main reason. The main reason is to be able to store massive amounts of data, and to scale it out and not be bottlenecked by a single server. So you have massive scalability, you have massive robustness. And anyway, so going back to in terms of the APIs, so what would the master APIs look like, and what would the worker APIs look like, as well as the client? So you can think of or what would the master API need to exhibit in order to allow for all of this to kind of work as a very top level. So we could say, for example, it would need something like get file. So that would definitely be an API request, for example. Another one could be list all files. Let's make this a little bit bigger. And another one could be delete file, and of course add file. So as the master node goes, those are the main kind of APIs it would potentially have. So when the client talks under the hood, it could ask, or essentially ask these APIs, and it would do the things that it needs to need to do in terms of updating its metastore and also pushing chunks to certain servers and whatnot. So in terms of the chunk servers or the workers themselves, what kind of APIs would they need? And I believe they could just pretty much get away, because they don't need to be that intelligent, because their purpose is just to store. And really, it would be to something as simple as put chunk, because they're not dealing with files. Put chunk. It would be something like get chunk, and also delete chunk. That's it. I think that's all they really need. They're not really intelligent, because there is no, the intelligence, if you like, all of the knowledge, if you like, is stored, because these are just dumb storage units, essentially, almost like So individually, this is what each of those worker nodes would do. All they can do is they can put a chunk, which is essentially here's a chunk of data, store it on the local file disk. Get chunk is given a chunk ID, give me back the data for that. And then finally, delete chunk is, as it mentions, here's a chunk ID I want you to delete off the disk. And with this combination of these 2 very high level APIs, that is all you really need. And obviously most of the logic really happens, most of the magic happens in 2 places really, is at the master server as well as the client. And as I said, the master server is just essentially a glorified in-memory database. Now, there is another part of it that makes all of this work, I believe, is that each of these worker nodes or chunk servers, they essentially have a heartbeat. So on a regular interval, so we probably need to add on here heartbeat. But that's more internal. It's not something that the client. This is not a client level, so it's more of a private API. So there's a heartbeat, and that's needed. That's very important, because that's how the whole thing becomes dynamic, and this whole elastic effect works. Because when a chunk server or a worker node comes online, it sends a heartbeat, because each of these workers, they need to know what where the location of that master is, what the IP address is. And once these workers know, they can send a heartbeat on a regular interval. And when they send a heartbeat, the master is aware of all of the available worker nodes or chunk data. Of course, if a worker node dies, then there will be no more heartbeat, or if the network goes down, or the that entire server crashes, or that node is, for whatever reason it fails, then the heartbeat will eventually drop off. And when the heartbeat drops off, then the master needs to then rebalance everything. That's obviously when something failed, and also when something scales up. If let's say 20 new chunk servers come online, then there'll be 20 new heartbeats going in to the master server. And once it gets that heartbeat, it can rebalance things and move the chunks around as needed. So those are the top level APIs that it really needs. Now, in terms of how something like this could be built, I believe, and this is my personal opinion, is that you could have a single binary. So like an isomorphic binary, essentially, that works in 3 different modes. So it's the same binary, but that there's no reason to have three separate binaries. And in terms of deployment, in terms of usage, it could be really, really nice. Or I personally like the idea of sort of isomorphic, not just isomorphic, it's polymorphic binaries, a single binary that does multiple things essentially. So because in terms of dependency, in terms of deployment, it's really nice having everything fully self-contained. So a single binary could essentially have 3 different modes, and the 3 different modes are here. So a binary could act as a worker node, or a binary could actually act as the master, or the binary could work as the client. So the client is, I think by default I'd probably have it as a client, so that you can get files, put files, list files and whatnot. The binary would behave differently or in different modes based on how that binary is essentially started up and what environment variables you pass it. So for example, the default, as I said, I would put the default as the client mode. And if you want it as a master mode, then you would have to set it up with maybe like you pass it as a key or something, some kind of specific unique key or something. Or maybe there's a tag that says this is actually, I want you to run in master mode now. And in terms of the chunk servers or worker nodes, you would need to pass the IP address of the master. So just by the fact that if the binary is passed a master IP address, then it will know that it needs to now run as a worker node or as a chunk server. If it's given a key, then it will know, yep, I need to boot up in as a metastore, as a master metastore server. And of course, if nothing is given, then it can just assume I need to behave as a client. So I quite like the polymorphic idea of that. And that's all for this particular session. And hopefully in a few of the other sessions, I'll actually start building this up and seeing how it works with a bunch of virtual machines. We can spin up, we could spin up, we don't even need virtual machines actually. We could make it much more lighter by spinning up a bunch of Docker containers, and we could simulate a very small cluster. Maybe we could have like a cluster of 20 or something like that, and we could then run this to see how it behaves. Of course, there's no performance metrics that you could do on a single server that wouldn't be representative, but it would at least give you an idea of how the whole thing works, and you could debug. It could be possible to debug that. And I think this is for me anyway, I find it a very interesting project to do. Then I have some further ideas what could be extended, but I really want to see, because I believe the metastore holding it in memory is really, really interesting, and the idea of having heartbeats to dynamically adapt that entire thing and make it completely automatic essentially. So there's not a lot you need to do, and I really love the idea of having a polymorphic binary. That the idea of you could just, in terms of setup, it's so easy. You just drop these on a bunch of servers, and they'll self-form their own cluster. So they will. It's very, very, very low friction in terms of getting a system like this up and running. It's very simple, and I could imagine it'd be very easy to roll this out onto something like a Kubernetes cluster or any other kind of cluster manager. And that is all for now. So until the next time, I'll see you on the next one.